I'm David Cohn. I'm going to be leading this is sort of a lesson 1, but we had a lesson 0, so the second lesson of a Postgres and Timescale Foundations course. Miranda, would you like to introduce yourself as well?
Yeah. Hello, everyone. My name is Miranda All, and I'm a developer advocate here at Timescale. Pretty much, I'm here to help facilitate questions and also ask questions myself, because a lot of this content I'm hearing for the first time as well. So number 1, don't be afraid to ask questions, because I will definitely be asking lots of questions. And feel free to, hop in, ask questions, give feedback, during the whole stream. So, yeah.
Yeah, and so I like to prepare a little something while we're sort of waiting for stragglers to come in. It's going to go a little shorter this time because we were a little late. So in this case, it's a silly poem, I guess, that you would call 𝗥𝗲𝗃, written about in the 1860s. For people who are learning English, and I was thinking of it for, I don't remember exactly why, but probably talking to someone who had some weird pronunciation and came into my head. And I was thinking about some of the ways that it might relate, but we'll go into that later. For now, I might even try reading a bit of it. We'll see how it goes. Dearest creature in creation, studying English pronunciation, I will teach you in my verse. Sounds like corpse, core, horse, and worse. I will keep you, Susie, busy, make your head with heat grow dizzy, tear and eye your dress you'll tear. Queer, fair seer, hear my prayer. Pray, console your loving poet, make my coat look new, dear, sew it. Just compare heart, hear, and heard, dies and diet, lord and word. Sword and sward, retain in Britain, mind the latter how it's written. Made has not the sound of bad, say, said, pay, paid, laid, but plaid. Have you ever yet endeavored to pronounce revered and severed, demon, lemon, ghoul, foul, soul, Peter, petrol, and patrol? Billet does not end like ballet, bouquet, wallet, mallet, chalet. Blood and flood are not like food, nor is mold like should and would. Banquet is not nearly parquet, which rhymes exactly with khaki. Khaki, parquet, whatever. Discount, viscount, load, and broad, toward to, forward to reward. Ricochet and crocheting, croquet. Right, your pronunciation's okay. Rounded, wounded, grieve, and sieve, friend and fiend, alive and live. Is your R correct and higher? Kate's asserts it rhymes with Talia. Hue and but hug, and hood but hoot. Buoyant, minute, but minute. Anyway, silly poem.
Wow.
It goes on for another it's like 800 lines. It's crazy. No, it's 200 something lines. It's
You gotta love the English language.
Yeah.
It just makes absolutely no sense most of the
So
time.
hopefully SQL makes a little bit more sense. And I hope that we'll get to a point where we get that, we get some of why I might do that today in this first lesson. Or I guess second lesson, but lesson 1, we've started numbering from 0, much like some people do with arrays. So who the heck knows what's going on anymore? And it's no longer February 15th, but I forgot to update the date. But because as I mentioned in the previous one, we have been giving these lessons internally as well. So I'm managing engineering education, and we're doing a lot of internal education, but we're also trying to make those all the stuff that we're doing for our engineers to learn more about Postgres and Timescale. A lot of people come from different backgrounds. They may not know some of this stuff. And so we have been updating, or we have been using this sort of format to give it first to internal and then give it more for an external audience, and really make it available to everyone and accessible for everyone. So anyway, we'll start off today with a scenario. So
love scenarios. Let's go.
Yeah. So you've been, I guess, Miranda, I can talk to you. You're now the inventory manager for your company. You can manage all the parts and make sure you have enough of them for all the projects that the company has. So what's the first thing that you might do in that type of situation? Well, I might make a list, right? I might make a list with some of the things that I need to know. So I'd go look in my stock room or whatever it is and say like, okay, well, I have some part names and I can count how many I have on hand. Maybe I look through the orders on my desk and I see how much I have on order. And then I might want to know also like the quantity that are committed to other projects, like to my projects. That would be useful to know, so I know if I need to order more or whatever else. That's going to be harder to get from my stockroom. So we'll leave that aside for now, and we'll just do the things that I can do for my stockroom. So these first three. So we might make a list like this, right? So write down in my notebook, okay, I've got parts, the quantity on hand, the quantity on order, and write it all down. I have some screws and nuts and washers and some panels maybe we used to put together with the screws and nuts and washers. Okay. So we can't figure out quantity committed yet. So we need to know projects. So the next thing that I might do is go to my boss and say, well, what are the projects that are around? Okay, so then my boss gives me a list of projects. Here we're keeping it really. Luckily, my company's not too big yet because this is if they made me the inventory manager, that might be indicative of.
You're trying to take my job. I was the inventory manager. Come on, David.
I didn't want to insult you though. That seemed rude. Anyway, so we go to the boss and we get a list of active projects. So, and with that, we might have a project name and a project manager. And I went from April to Zoe here. Zoe's my fiance, and I figured that was fun because it was A to Z. So these are our projects from April to Zoe. So now we go to each of the project managers and we say, okay, well, what parts do you need for your project? So they give us a list of the commitments that they have. Say, okay, so for the cube project, we need 6 panels and 24 screws and 24 nuts. Awesome. Don't think too closely about the geometry. Really not trying to tell you how to make a cube or a pyramid. Right. Anyway, so for the pyramid, we only need 4 panels and 12 screws and 12 nuts and 12 washers. So now we need some washers for that one. So we add that to our list of the commitments that we have for our inventory. Okay, so that's awesome. We now have a few lists, right? But now we want to ask answer that question that we really need to answer if we're going to be a good inventory manager is like, do we have enough of the parts? Okay. So what we would need to do to answer that is first add all of the commitments that are like each other. So for panels, we would look and find, okay, I've got 10 that I've committed to. And for screws, okay, add those up. That's 36, so on and so forth, until we've added all the different things. And then we can compare to our original list. So I might match our panel to panel here, and I can even notice right then that, there's 10 committed and 5 on hand, but it might be easier to see this. I didn't have to try to match and crisscross everything and match this way. It might be easier to say, well, maybe if we combine the rows between these two lists and make a new list that has, everything aligned right. Okay, so I can do that. And now I've lined it up and I can see that, I have a problem here. It's a little easier to see in this view, right? That I don't have enough panels. I don't even have enough on order if I were to add that in, right? So that's, simple scenario of something that we might do in a job. Obviously, it's a very toy scenario, but something useful. And you've just built your first database.
Wow, that was easy.
You've also performed your first join and aggregate. And so part of the reason that I present it this way is that I want, as we get into this, it can seem all really abstract, but fundamentally, these are the kinds of operations that the database is doing. We're making lists, and then we're putting them back together, or doing summing operations, or doing whatever else. So we're just doing that on a larger scale and with a different type of language to express it, with some more built-in controls around how that can happen and how that works, right? But fundamentally, these operations that we just did are almost exactly what the database is doing on the other end. Okay. More complexity on top of that, all sorts of other stuff, but just to keep us grounded. So let's
It is
database
nice
apply
to
it.
see it. It's kind of the core of the database that, it's relatable. It's things that we already tend to do.
Yeah.
So that's cool.
And I just want to I want to concretize it because it's really important that we don't get so lost. And this goes back, and we'll cover this more in a little bit. This goes back to all the terminology and sort of like the English pronunciation, right? There's a lot of new words and stuff like that,
Right.
and it can be very confusing. But fundamentally, the operations are relatively simple. We're layering on complexity on top of it. We're able to do much more powerful stuff. But fundamentally, the fundamental set of operations is relatively simple.
Hmm.
Okay, so let's translate this to SQL. And the first thing we'll do is we'll start setting up the structure of the tables, right? So that was the things that we were going to track. And in this case, it's just a create table statement. This is relatively, um, I guess, intuitive in some way, right? You're creating a table and you're listing the fields that we're going to track, much like we said we would when we were talking about this is a list of things we might want to see. Okay, so we create a table called parts. So we name the table. We have a part ID. It's a big serial, and that's something that automatically increments. So that's all you need to know about that. And then we have a part name, and that's a text field. So a table definition basically follows this type of structure where we have a name, and then we have the type, the data type that it's going to be. We'll go over that more. That's essentially how these table definitions work. So I've defined each of my tables. Our line number became this ID, and this is this automatically incrementing ID. We might use that at some point in the future, but we don't need to. We don't necessarily need to have a big serial ID. That's something that sometimes happens. We'll talk more about that in future lessons. So for now, this is just a very simple way of creating some tables to start putting together this data.
And just this is more for people that are very new to SQL.
Yeah.
But right, each of the part ID, big serial, part name, text,
Mhm.
that row in this is actually referring to a column that you're going to create. And
Yeah.
that data type is what you can put into the column.
Yep.
So just
And we'll cover some of that as well. One other quick thing to note is that everything ends, by the way, with a semicolon. So you can see that too. That's how we define the end of a statement here.
I also really like that SQL, and I'm sure that, as we go through more SQL code today, that it's pretty intuitive, like create table. It's like you're creating a table, which I
Yeah.
think is cool.
Yeah. So these sorts of things that I don't want to go too in depth on these statements for now anyway. There's a lot of complexity that we can add into a create table statement, but at its simplest form, it might be something like this. Okay, so now we can insert some data into the tables, right? So we had our table created, and I just put that there. You don't actually need to do it again every time. I just wanted to put that there so that we would have the structure there. Now we're not going to insert, and then we write an insert statement. So we say insert into, we name the name of the table that we're inserting into, and we're going to have some values, right? So screw 100, 200, nut 105, 95. Those are the ones that amount on hand and the amount on order. And so these parts, you'll see that we named our columns in our insert statement. So you can also do that. You can name our columns. We don't actually include the part ID. That's going to be provided automatically because we said it was a big serial. Great. So we now have an insert statement. You'll note that, by the way, text is in single quotes, but numbers are not. And yeah, and the thing that I just said that I always forget, sometimes I have a slide to explain the thing. Anyway, so awesome. So now we have data in the table. How do we look at it? Okay, so that's a simple select statement, which allows us to get data out of a table. So we have a from clause, which says from parts. That's the table that we're working with. And we have our select and some names of columns. Now, one thing to just note is that if you were to refer to these things with a very careful naming scheme, it would actually be parts.part ID, parts.part-time, etc. And that allows us to identify it and use it like very accurately. But if it's the only thing in the from clause, we don't need to worry about that.
Yeah, and it's kind of like saying like select from parts table the part ID column, you know, and just
Exactly.
kind of like table column, which
Yep.
yeah.
Cool. So then we can add some more data. We can add in the rest of our data. So here we have our projects information that we had. We know like April was working on the Q, was the project manager for the Cube project, and Zoe is the project manager for the pyramid project. Awesome. Lovely. And then we have our commitments, right? So all of that data can just go in the same sort of thing. Notice that I didn't use so in the previous ones, I used these names. Oops. Previous ones, I used the names inserted into projects, names of columns that I'm inserting into. And that's because I'm not inserting into the first column project ID, which is a big serial and it's going to get filled in automatically. But if I am inserting into all of the columns like this for commitments where I don't have an ID with it, well, then I can just say insert into commitments, and I'm inserting into the whole thing, and I'm specifying all the columns. If I don't do that, it'll throw an error. Just something to know. Cool. So now we need to ask that same question again. How can we tell if we have enough of all the parts? So when we did this last time, we first added all the like commitments, right? And we developed this total commitments bit, which was the sums of the quantity needed. Which I called quantity committed over here. Whatever. Same idea. So we can write a simple aggregate statement. And here that idea of saying we're going to find all the like commitments, well, we're doing that on part name. We're going to find the like ones based on part name. And that is in our SQL statement, that's our group by. So we're grouping by part name, and we're finding the sum. And we also have to select the part name so that we know which one it appears. Okay, so that's our aggregate. We call this an aggregate. We could also, but the thing is, we might not want this to appear as sum. We might want to call it something a little bit more descriptive, especially because we might have multiple aggregates potentially in a select statement. And so we might have an alias for a column. So instead of calling it sum of quantity committed, and we just see sum, we'll see sum of quantity committed as total committed. So we can alias the column name, and then it'll appear as total committed below. Nice. Now, if we wanted to alias the whole select statement, sort of like we did here, right? So we actually sort of created this separate table that had this information. Well, we could create a view. So this is one way of doing that. There are different ways of aliasing select statements, but this is one way of doing that. We could create a view called total commitments. And that allows us to refer to this select statement by that name, total commitments. And so if I select star from that, right, which just says select everything, then I could also say select part name, comma, total committed, and I would get the same thing. I get the same thing as when I just ran that select statement. That's what a view does, is it allows you to just call a view by another name, or call the select statement by another name. Okay. And now we have to join rows together, like we did, to compare our results. So what we were saying, right, we were comparing it to our original list, right? That's how we were doing this join. We were matching on part name. And we were trying to get this sort of combined thing where the rows are nice and across the way so we could see it more easily. And that's exactly what a join does in SQL. So we say select our tables, we join, and then we have an on clause that tells us about how that join is happening. So that join is important. We have our on that says this is the condition that we have to beat in order to make our rows match. And in this case, it's that our P, which is referring to parts, and I'll go over that in a second, part name equals total commitments part name. And you'll see here, if I look across, that the part names match across the rows. Useful. That's how we join them.
It's almost like a mapping. I don't know. Like I feel like I almost think of it as like, yeah, like mapping instructions.
Totally. Yep. And the notice here that we did that same alias thing that we did with the aggregate. We did that in the from clause. You can alias in the from clause, so you can use this as. By the way, you don't always need to include the as. It's not necessary. You can just say parts p or part name p name, right? If you wanted to rename that. So you won't always see the as statement, but if you see the as statement, I find the as to be useful in at least some situations. It just tells me this is an alias. Otherwise, it can sometimes be a little bit harder to tell, especially if you have longer names than this, like the space, or if you're missing an underscore or whatever else. Anyway, I tend to use as more than some people, whatever. But we can alias in the from clause. We could also, and you'll notice when we do this that we do that dot notation. So we say as p, and then we can say p dot. So we have to tell the system where the columns are coming from in order to know that we get the right one. So we see the same thing here. So we have our P, we have our TC, total commitments. So P is parts, TC is total commitments. We could, of course, write out the whole thing, right? We could say parts.part parts.total commitments.part name, right? All of that, we could write it out, and then we wouldn't alias these things. We just write out the whole thing. It tends to get a bit verbose, and I think it can be harder to read, especially as you get to longer table names or view names like this. So often people will alias. But why do we need to do this at all? Well, it's because otherwise we might not have unique names, or the system might not know where to pull a certain column from. So especially when we have these repeated names like part name, which we're joining on, the system needs to know which one I want. Now, in this case, there's an equality condition. They're the same, and so we might be able to do something about that, but we'll deal with that later. For now, let's think about, are we going to that question that we had, which was, well, where do our commitments exceed what we have? And so there we can use a where clause, which filters the rows that we return, right? And you'll see we have an operator, which is greater than in this case. So where total committed, right? So the amount that we have committed is greater than the quantity on hand. And we can see that is true here. Now we could also do where total committed is greater than p dot quantity on hand plus p dot quantity on order, if we wanted to be, optimistic that everything's going to come in on time and all of that. So we have an operator in our where clause. You can combine multiple things into a where clause. We could add more things using and or and other stuff. We'll go over more of that later, but I wanted to just sort of describe some of this in broad terms for now. So where lets me see just the rows I want. What if I want to see different columns? Well, in this case, for instance, we might only want to have one part name column, because we don't want this repeated name here. It's just duplicate information. So in that case, we can just leave it out of the select list. So our list of columns that we are selecting determines which ones we see. So I can just do that, and now I can cut that down and only see the one part name. Lovely. And so this is really like the view that we wanted from the beginning. This is this is what we got to, is this part name, quantity on hand, quantity on order, total committed. But we did it having multiple lists. We had, and we're doing a join, but we built that up in a pretty sort of quick way. I know that it's a lot to cover. We're going to go over some things now. I'm going to call it terminology, but these are sort of alternate names for some of the things that we're talking about. So we refer to them as rows and columns. What else do we call them? Because one of the things that gets confusing in my mind when I was learning SQL is that not all the terminology was constant. And so I want you to be able to go in to the documentation or someone else's course or whatever else and pick up the material and not have to do a lot of like, wait, what? All of this is, and use context clues to try and figure out what we're talking about. So I'm going to try and introduce a little bit of other terminology so that you have some context, right? This is going back to this, like, there's a lot of stuff here. Sometimes these are synonyms, whatever else. Like, there's a lot of words. How do we get our heads around it so that we can like really understand some of the ways that people refer to things into a database? So our first thing here, we call it a table, right? Our list of things. Usually it's not called a list in a database. We are usually to call it a table or a relation or an entity. And those come from various places, which we'll talk about in a little while. For rows, we might call it a tuple or a row or a record. If I'm missing any, Miranda, that you can think of off the top of your head, please let me know. I think that I came up with a fair number of synonyms. I'm sure there are others that I'm missing, but usually these are some of the things that we refer to. For columns, right, we might call it a column or an attribute. Sometimes you'll hear the word domain. That has actually technically a specific and different meaning in Postgres. So I usually won't use domain to mean a column because in Postgres that has a slightly different meaning. And then field is another one that we can use in that case, and that comes up every once in a while, though a little less frequently, I'd say. So what about the values, like the individual values? If I'm talking about the values in a row, I might call it a datum, a value. I might call it an attribute of a tuple or a tuple attribute, something like that. Those are how we'd refer to the individual things. What about values outside of the context of a row? So if I just do something like select 105 or our values statement, right? I might call them datum sometimes. Value totally works, right? That value statement, right? But to provide literals. Often they're called literals or scalar values to distinguish them from ones that sort of occur in the database, but rather they're ones that you're providing as the user. So usually you won't hear that called a tuple attribute until it's really in the table itself, and you're referring to it in the tuple context.
Oh yeah, I was just gonna say that, yeah, since tuple, we sometimes is referred to the row. Like if it's not in a row, then it wouldn't be a tuple attribute.
Exactly. And to be clear, like the attribute usually refers to the all the values in a column, not the specific value in a given tuple, though it can. And that's why you sort of say a tuple attribute, because then you're saying, well, we're referring to a single value rather than the columns or the row. So they're sort of collective nouns that then you can clarify and make more specific. Okay. So one question is that you might ask then, like, does that terminology stay the same once you've done something to the data? And the answer is mostly. So like, let's consider joins. So this would still be called a tuple or a row or a record, right? That's totally fine. This is still called a column or an attribute or a field. All of those things stay the same. However, do we think that this is called a table? The answer is not usually. You could call it a table, but usually you wouldn't. Usually a table is sort of reserved for the stuff that's actually stored, not the stuff that's joined. It still is definitely called a relation. In some cases, you can call it a view. I almost certainly wouldn't call it an entity. Maybe some people do, but I wouldn't. Maybe
You're
if
just
it's a
judging the
view,
people that use entity. Okay.
maybe if I called it a view, if I made it a view, I could call it an entity, but unlikely. Anyway, once it's joined, usually like entity comes from entity relationship theory, and so like the relationships. Anyway, doesn't matter. The entities usually refer to the base tables. And so the other thing that we can call this is a join relation. We make this a little more specific, or a join rel for short, right? So you'll hear that sort of stuff every once in a while. You'll hear about join relations or join rels.
I've never actually heard join rel.
Yeah, certainly if you go deeper into the Postgres code, but even like some people just throw that terminology out there, and they're like, but so in general, it can be useful to have some of these shortening bits, because I was like, oh, I get it now. It's also some of the ways that the catalog or the Postgres catalog refers to some things. So base relation, for instance, or base rel, that's the one that's actually stored on disk somewhere. You'd also more likely hear that called a table.
Wait, so sorry. The last one, the base rel.
Yeah.
Which explain this again.
Yeah. So this is our parts table. Which it seems like I may have switched from singular to plural or plural to singular at some point, but whatever. Cool. But yeah, so this one would be called a base relation. So it's sort of you have a join relation, which is at a higher level. That's whereas a base relation is the one that's actually stored on disk, right? So a database, it's like this is the base, and it's also like the lowest level, and where the data is actually stored or represented.
So how is this different than the table?
Yeah, I would also call it a table.
Okay. Okay.
But sometimes people will use table to refer to sort of anything, or like this is also, you can call this a relation. That would be fine.
Okay.
But I can also call the joined thing a join rel. I can't call this a base rel.
Right.
Base relation.
Right. Because it's not being stored on the disk. You're joining two stored.
And I can't call this a join relation. So I just wanted to like call out that this is a very specific way of referring to the thing. And when we want to make distinctions between those things, we don't always want to make distinctions between these two classes of things, but sometimes we do. And when we do, this might be how we do that.
So would it be true that any stored table, any table that's stored on disk would be then a base relation?
Yes, with a star, with an asterisk.
Okay.
Which is that a materialized view or something like that might get a little weird.
Okay. Okay.
But because it's derived data, but it's also still stored on disk. So that
I was curious about materialized views.
But that's, we'll
I feel like
we'll
it's
get
like
to that
different
later.
Than a table. I don't know.
It is different than a table. Yeah. Anyway, that's a discussion for later. I think let's not go too far down that road.
Don't want to be too hasty.
So let's continue with our terminology discussion. I know it's a lot of terminology. I'm partially doing this. We're going to provide the slides under the in our comments, and we'll provide a link to that on the YouTube comments, I think. And so you can go and refer back to this and go look at some of this terminology if you want to. If you're like, wait, I'm confused. What does this word mean? Maybe this is a good place to go. We're also thinking about making like a glossary so that you can start looking up some of this and finding just quick definitions for this stuff. So, okay, so the SQL statements we wrote, let's talk about some of the terminology that we might refer to those or parts of those. So one is DDL. You'll hear that thrown around a lot. It means data definition language. And so that's anything that modifies the structure of the database. So tables, relationships, indexes, things like that. Constraints.
So is that a I guess this is a historical question or history question. Is the data defined language, is that like an old SQL thing or like I'm just curious
data definition language, not data defined language.
Oh yeah, sorry.
So I don't know exactly where that came up first. I've delved into some of the history, but I'm not sure exactly where that came from. I think it is something that came from SQL.
Okay.
But
I was just curious.
Yeah, and so then you'll also hear it referred to as like then the next. If you hear something about DDL, you might also hear a little bit about DML, which is there's a slightly different. So then there's a different class of things that it refers to, which is like inserts, updates, deletes, and they modify. It's something that modifies the data. But you'll notice that this is modifying tuples in a table. It's not modifying the table itself. So I'm not like saying alter column or whatever else. So usually these start with insert, update, delete. There are some slight exceptions, but mostly that's what's going on there. So if you hear someone refer to DML, that's what they're referring to. You'll also hear every once in a while VQL. right? So data query language, right? And technically all of these are parts of SQL, but usually this is just referred to as SQL. And then you have DDL and DML.
But you won't hear DDR. Dance Dance Revolution. I'm sorry, that's the first thing that came to mind when I saw DDL. I was like, oh, DDR.
Yeah. No, and though if you want to write an interpreter from DDR to SQL, that would be funny.
That would kind of be amazing. I feel like this is a project that I would 100% get behind.
Next hackathon, Miranda. You can do whatever you'd like.
Coding with exercise. Come on. It is brilliant. We could totally do this. DDR SQL. I love it. DDR DQL. You could go.
Oh man.
Sorry, tangents.
So anyway, the DQL, the data query language, is basically anything with a select. Sometimes selects have side effects. We won't talk about that right now. If you know some things about TimescaleDB, we have some things that you are actually running in functions, which then can have side effects. But if you're just doing basic sort of stuff where you're selecting columns from tables and not calling functions on them, then this is not going to have any possible way of doing modification of the data or changes to the structure of the database. And so usually, even with functions and other things, they don't do that. There aren't really side effects like that. So basically, it's something with dyslexia. So now some like terminology of other stuff. We might call this the target, like the list of columns in our select clause. We might call it a target list. It's also known as projection. So our projection set, which is, we'll explain a little bit about where that comes from in a minute. Right. They also might be called fields or attributes, as we talked about with columns. It's also known as the select clause. I probably just accidentally duplicated that slide and forgot to remove it. Sorry. So, and then we have our from clause, right, which also might include a rel list, which I don't know whether there's usually, which is a list of relations.
Okay,
right?
I was going to ask, is that like short for relation list or something?
Yeah. Yep. Right. So it could be parts P, and then each of these is technically and join. So parts and total commitments are our relations. That would be in the rel list in this case. Now, and this would get expanded as the query is being processed, right? So our rel list would actually expand. For instance, as you're going down views, like you get to base relations eventually. There's different ways that happens.
I mean, that makes sense. Like, it's like the things that you're relating together, whether it be like the base, table or like I don't know. That makes sense.
Yeah.
Relation list.
Yeah. And so then you have inside of a from clause, you might have join clauses, which might have our qualifiers and conditions.
Or multiple join clauses.
Yes. We also have a where clause, is also known as this operation is also known as restriction. Like, so it also can be called a filter, though again, this is another term where it has a specific and different meaning in Postgres. And to an extent, some of these things also have that meaning in the SQL standard. Some of them it doesn't. Postgres usually follows the SQL standard pretty closely, though. So that's just something to know. And of course, aggregates, right? We have an aggregate, or an aggregate, sometimes called an aggregate function. Things like sum, count, average. And then we have a group by clause, which includes grouping columns. And you can switch out words for that, for adders, something like that, whatever. Just, again, going through some of the different ways that we might refer to the same sorts of things. So like I said, this can be a little bit overwhelming, right? So first off, I'm assigning a little bit of homework, which is go through what we just did here in terms of creating tables, all of that stuff, and make your own version. You can be this problem, it can be some other problem. I would love to see other problems here, like other sorts of approaches.
That'd be super cool.
and install Postgres however you want. I'm going to leave that as an exercise for the watcher. There's lots of different ways to do that. Postgres.app might be a good one if you're on Mac. That's what I use just to do a quick setup. But there are lots of different tutorials about that.
Docker.
Docker, yeah, all sorts of stuff there.
Many containers.
But I want to keep going for a minute. So we talked about this poem, right? The silly poem. And like the thing that we can kind of glean from it is that English spelling and pronunciation and all of that seems a bit of a mess, right? And then we can put it into a little bit of context, right? And maybe we can help understand some of this stuff and all of these terms that we just went over in SQL if we understand some history. So first, a little bit of history of the English language. Like, how does this help us understand, or at least know a little bit about what's going on here? Well, first off, you'll notice in the history of the English language, and I have to have my qualifier here. Really, I'm not a linguist, so I listen to a podcast.
So I do know. Wait, which podcast do you listen to?
I listen to various ones. I used to listen to, anyways.
The History of the English Language?
Oh, no, I didn't listen to that one. That sounds
That's
fun.
a great
You
podcast.
probably know more about this than
really
I do,
good.
so please fill in.
No.
But anyway, one of the things that I noticed when I think about this is, there were a lot of invasions. So, like, first off, there are, like, the North Sea Germanic peoples, which go and, like, settle the English Isles, and there's some, like, already maybe some people there, and who knows what happens there. They're certainly intermixing, maybe conquering. Long time ago. We know that the Vikings invaded and the Norman conquest, and then also the English, as you may or may not know, had a bit of an empire. And various other folks were like learning English. So every time that happens, you have non-native speakers learning a language. And when non-native speakers learn a language as adults, various things happen to it. And this is, like, as far as I understand, it's something interesting and fun that happens in linguistics. Like, people know this, like, you see the case system break down. Like, all the complexities of grammar tend to break down and things get simplified a lot. So Old English had a case system and, like, all sorts of craziness. If you've ever studied Latin, like, all of the nouns were inflected and whatever else. I think there was also gender somewhere in there. All that goes away as the successive, or most of it goes away as all of these successive conquerings happen. Now, there are little bits and pieces, and probably some of the irregularities and things like that come from some of those bits and pieces that were left over. And did you have more to add on that? Because I
was just gonna say, one of my favorite examples that, like, blew my mind whenever I was listening to this other podcast was so the I guess it was technically the Proto-Indo-European language. The name for, like, the god was Zeus Pater, which is sky father was, like, the translation. And it's cool because, like, you can see how it transformed over time in, like, Greek and Roman languages and, like, lore, because you have Zeus, who was, like, the sky god, and you have Jupiter, which is, like, the sky god. And it actually is, like, both of them come from Zeus Pater, Zeus, and then Zeus Pater changed to Jupiter.
Yeah.
Just cool. Like how the language changed, like the certain sounds they found in linguistics will, like, switch over time as people.
So there's,
like, bring in new
we
influences.
actually see here the great vowel shift is another thing that generally, like, and that happens in a, anyway.
Anyways, fun thing.
Yeah, no, totally. Thank you. By the way, the other thing that I wanted to mention here is, like, in the middle of a lot of these changes, we have the printing press coming around, which suddenly, like, now spelling and standardization of that starts happening, but it's, like, during a lot of different changes in the language. And so some of this pronunciation and, like, all the crazy spellings come from this history. And so we can explain a little bit of what's happened to English and all this crazy pronunciation with some of its history. And so I wanted to give a little bit of history, which might explain a little bit of where some of these various terms that we just went over and different ways you might refer to things come from. as well as just giving some context for where this developed from. So we talked in the previous lesson, we were talking about the 1960s and 70s, and we talked about some of the early database systems that provided certain types of guarantees. We talked about asset guarantees and what they did. So these come from a few of the major players, things like IBM's information management system and the System Development Corporation, which I think they died. Honeywell, though, had like Codicil. Honeywell, I think, still is around a bit. Maybe not as much in the database world. They've sort of left that, but IBM is still around, and they still have IMS. It's still a hierarchical database. Some banks still use it. So like these things still do exist. But the relational database eventually sort of superseded them. And just to be very clear here, right, before these sort of early systems, businesses were writing their own transaction managers. TXN is an abbreviation for transaction. And that was buggy, slow, difficult, rather annoying. And so these were still a huge advance over the state of the art, right? So you now didn't have to devote developers to doing their own transaction management and all of that other stuff. You could just rely on the system to do that. And so let's look at, though, how these hierarchical systems might have worked. So we have that same scenario. We have parts, part numbers, all of that stuff. But here in a hierarchical database, the hierarchy essentially defined the relationships between things. So for instance, we could have something like the inventory manager, right? Their view might be essentially that projects are subordinate to parts. So I have my parts that I am managing, and then I have projects that need parts. And so the projects fall below parts, but they're in the same file, right? So again, we had file, they usually had a segment, and then they had fields. The fields sort of defined what we call columns. But the fields were sort of potentially more complex. You also had these children, right? So part and a project was essentially a child of part, and you could have multiple projects inside of here with all of the information. So, and they sort of had subfields like this. Okay. So you could also look at it the other way. Maybe it's the project manager's view. So here parts are subordinate to projects. So as the project manager, well, I care about the project and all the parts that it uses, not the other way around. Now, you could also have some other views like, the parts and projects are peers, and then we have another version of project part. So like the inventory manager might have this, and it's like, okay, well, I have one separate list of projects, and then I use the project number to refer back to that and have the quantity committed inside of parts. Again, fundamentally here, the relationships are mostly defined by the hierarchies. And the same thing with this other one, which is like sort of just the equivalent one is but flipped, where now the project manager has parts again subordinate, but only in this more minor way. And then you can also have another version which begins to look much more like the relational model, where they're peers. They're all peers, and we have commitments now. We define this commitment file that has its own fields that refers back to the project and part numbers and the quantities committed. So that's lovely. And we're getting somewhere closer to the relational model, and you could build it sort of in this hierarchical system, but it might not have worked that well. First off, because all of these are valid. All these are valid ways of representing the data inside of a hierarchical system, which means that if I write a program to work on one, it won't work on any of the others. Or not necessarily anyway. Might, kinda, but usually won't. Right? So if I write a program that works on the inventory manager's view, or in this one, like it won't work on the more equal view at the end. There's no way for it to know that it needs to go to the other file where commitments live in order to do that. It will go through parts, look for a project, see that there isn't one, and say, whoops, and stop. This is partially because like the programs actually needed to know a lot about the internal storage structures. They needed to know that this file existed. They needed to know maybe that an index existed. They needed to know exactly what was a child, et cetera, et cetera, et cetera. So it was highly dependent on the way that the program was built. The other thing that was really important about this is that access was really record by record. So if I look at this field, what I would probably do in order to go through this file what I would do is say, okay, I would write a loop. I would go through each part in the file F, get the next one, and then each project inside of that, I'd get the next, and I'd add up my commits. Right, so that's how I do my aggregation in that view. Now, what if we think about how we would do and so that's fine. That's not crazy. Does this make some sense, Miranda, by the way? I don't know, like sort
It
of,
does. Yeah. I think it would be cool if in the future, like seeing, I don't know, seeing it connected to, seeing it with both
yeah,
views.
that's fair.
Because I think that
Yeah,
that probably
so,
helps. But I'm following. Um,
well, so yeah, so let's just like
let's
keep
go
this
through the
up and
two
sort of
steps.
discuss as we're seeing. So for each part in F, right, we go through the part, and then we look for the subordinate thing, a project, and then we're going to add up our commits. So each part, project, look at the quantity committed. Okay. So that's okay, but now let's think about if I did it from the project manager's view. This gets a little harder, right? I can't do this aggregate operation so easily. So now if I go through this view, I have to go through each project, and then in each part, I need to get the part and maybe hash the name of the part, and then I can add it up, and then I need to store it somewhere else. And like, so there's this whole thing that needs to happen because I need to go through like the first one. It was really easy because it was just arranged by part already for me. But on this one, it's much harder because like it's arranged by project, and I have to then add up all the parts across different projects. I'm not adding it up based on project. It would be easier if I were adding it up based on project. So you can see that there's this asymmetry. For projects, it's very easy to write this aggregate in this view. For parts, it's not. And in the other view, it's easy to write it for parts, but it's hard to write it for projects. So, and it was very heavily dependent on the implementation, right? Even the order in a file might matter to some of these programs, which really got them very entangled in the way that the data was stored.
Overall, these seem like pretty not ideal methods.
Yeah. So
What
in
I'm getting.
1970, a guy named I forget his actual first name, Edward Codd. I believe it was Edward. Codd comes along. He's at IBM Research, and he writes about a relational model for large shared data banks. Right. That's the name of this paper that sort of kicked off the relational database field. It's also to an extent where this example is pulled from. Right. He's giving this example and trying to explain why he thinks this is his way is better. The basic gist is that you're storing data in a very simple structure, right? The table that we talk about here, right? Which he calls it an array representation, right? Because it's rows and columns, and he's coming from a math background. We're avoiding these nested hierarchies that are common in hierarchical databases that make things rather difficult to work with, right? So it really looks a lot like this final view. And that's basically how this would work, right? We also don't have this reference back to file anymore, though. When we start going over to the relational view, we don't need to know as much about how things are stored. We might also have this idea of the relationships, and this is part of why we call it the relational view. It's a relation. This is where the tuple terminology comes from. He's really working in set theory, was a lot of where his background was, and so some of these words are pulled from set theory and used very heavily there. So we now but he talks about then relationships, which are defined by primary keys or foreign keys. We no longer need to know exactly what the index is, right? In the old systems, you had to know about the index by name, call it, say, I want to go access this row using this index, using this method of retrieval, then I can go do that, right? We don't need to do that anymore. We just define it at a much higher level. And the basic goal is we want to avoid encoding too much language or too much logic about the data in the physical representation on disk. And we also really want to access it through a set-based language, right? It's much more high level than what we were doing when we were processing row by row. But he was a mathematician, and his
Whoop, whoop.
language was a little difficult. for people to understand. I don't have an example of it here, but it was, I started reading the paper and my eyes started glazing over. I'm not a mathematician. I sometimes have trouble with some of the abstract notation.
Yeah, set theory is actually one of the areas that I studied.
Hmm.
And it can get it, like, if it's like a language. I mean, just like with SQL, once you
Yeah.
get into heavy, like, theoretical mathematics, you have to learn the language before really being able to grasp it as much. So yeah, not
Yeah,
the
and it can
easiest.
be, and it can just be like, and it's very terse. Part of the thing,
Mm,
like, is that it's very terse, which can be fine. It encodes a lot of information, but it can also be just a little bit harder for people who aren't mathematicians to like grok. So anyway, this leads to a multi-year debate in the database community between the hierarchical folks, the people who want something like 𝗥𝗲𝗹𝗃, which is a network database. I'm not going to go into those; they're just like a crazy mess. And I kind of
now I'm
understand how they work, but
curious.
there's just like there's a lot of crap that was going on there. They were still row by row. The thing that like mainly links codicil and hierarchical databases versus SQL and the um, the sort of more relational approach um, is that the codicil and hierarchical have this procedural rather than declarative approach, right? Procedural means they're doing this for each, right? We're going to go through and we're actually tell you how to go and do the lookups of data um, row by row, uh, doing our aggregations, et cetera. Whereas SQL says, give me this, right? Do this thing for me. This is what I want. You figure out how to do it. And I think in the end, this is really why SQL wins, is that this turns out to be much better in terms of ability to optimize, where you can use systems to optimize it that, unless you're a really good coder, you're not going to be able to do it. It's a lot simpler to write because you don't need to do every operation. It's a lot less brittle in terms of implementation. And so that declarative versus procedural approach really has a big impact. Right. So we said that SQL wins probably because of this shared procedural, the declarative approach rather than the procedural approach. And Postgres, I will say, comes later. I don't have time to go into that history. We might do that at some point, at least some of it. But for now, if you want more information on some of this, you can take a look at Stonebreaker's paper, What Goes Around Comes Around, from like 2005. It's a lot of this history, at least his view on it. So again, reminder, your homework is to go through what we did before, make your own version. We'll work on some of that. We'll build on some of that stuff next lesson, and
And
start
what we did
thinking a bit
before,
more.
you mean setting up kind of tables and
Yes.
joining them and things like that, right?
Yeah, exactly. So just going through this sort of example. Let's see. Yeah, I mean, I think that it would be um, great if you can get to the point where you can do a join of some sort.
Yeah.
And one of the things that I'll probably do in a future lesson is like go over how you can read, how to read the Postgres documentation and other sorts of stuff. But I think it would be great if you can just start to try and figure it out yourself, um, with a little bit of guidance, but not like this is exactly what you should do. I
Mhm.
want to keep it a little bit open ended. If you have your own project and you want to like start trying to do a little bit of this yourself, I think we're going to be doing a little bit about data modeling next lesson. So that should be an exciting thing to start going into. But we're going to try and really bring that together. So I think that's what I've got.
Awesome.
I didn't really leave time for questions this time. I don't think there were that many people here, but hopefully people will be watching the replay. Um, and yeah,
I think we only have one person watching right now. One lovely person that is watching right now. Do you have any questions? Or does anyone else do? Yeah, hopefully folks will feel comfortable to leave questions on the video later on. We love feedback from you all. So please feel free to leave comments, questions, anything, because we're here to, make great content that is helpful for you. So
Yeah.
helps to hear from you.
No, like really truly, we love feedback. This is probably not the last iteration of these types of lessons that we're going to do. We're going to keep working on this and making this better, and anything you can do to help us, what you're getting, what you're not getting, all that stuff will be really helpful. We're trying to keep this available to anyone with sort of any level of experience, but also hopefully providing some context for people who even have some experience with SQL. So I wanted to try to make sure that I got to some of the history, some of the terminology, all of that sort of stuff that maybe people aren't quite as familiar with, but I think is actually really important and really helpful for understanding this well. So
Totally.
hopefully that's useful for you.
Thank you all for joining us. Super fun. Yeah. And thank you, David, for putting together this awesome presentation. Really love this series and very excited for the many more to come. Yes.
Yeah, very exciting. Anyway, I think we are over time, but this was
Mhm.
really lovely. Thank you all for joining, and whoever's watching in the future.